And let's get into a fun topic. So I'm going to go to edge-based computer vision here. And we'll go to topic 2, lecture 2. And we'll get into some of these emerging computer vision technologies and talk through them a bit. So one of the things that's interesting about edge-based computing, emerging computer vision in general, and the combination of all those is that no one has really got a perfect solution yet for how to build products. And one of the things that happens when you're first getting started is that you'll have some interaction with deep learning. So if you want to build a computer vision application, most likely you're going to need to get into some type of neural network in order to do something interesting. And one good resource that I like is this article by Lex Friedman here, where he talks about the deep learning basics and also an introduction and overview with TensorFlow. So he goes through and has a topic or lecture where he covers these topics, including deep learning, deep reinforcement learning, human-centered AI, and self-driving cars. So I think this is a good overview of some of the topics. And another thing that he goes into is the different components of deep learning here. And in particular, some of the things that he talks about are these neural networks are either encoders, decoders, or a combination of both. And so an encoder finds a pattern in raw data. A decoder generates high resolution data from those. And one of the pieces that he gets into here is this distinction of these different categories of deep learning. So you've got supervised learning, which includes things like a feed-forward neural network, a convolutional neural network, and in particular, the convolutional neural network is the one you'll see where people have an image. They use this convolutional encoder, which will come up with a representation, and then there'll be a prediction that comes out of it. And the word supervised is an important thing to define, and that means that you have already basically have the labels created for what you're training. So you know what the right answers are, and you're putting it into a convolutional neural network and then training it on the right answer. So supervised implies that there's historical data that's correctly labeled. And then a recurrent neural network is a type of neural network that deals with sequences. And the reason why it's able to deal well with sequences like speech or text or maybe time series data is that it is actually the encoder is recurrent. So it goes back and forth on itself, where these other networks, they just go from left to right here. And then there's some other capabilities here, encoder decoder architecture. And then there's the unsupervised learning. And the unsupervised learning gets into some of these interesting techniques that we see, like generative adversarial networks, where you can generate and figure out whether something is a real or fake prediction. And that you see these used in all kinds of face swap videos and things like that. And so the key difference here again is that we don't know what the right answer is. We're actually just doing basically pattern recognition and trying to identify things. Now, reinforcement learning is a third type, and the reinforcement learning, the big deal about that is that it's a feedback loop, and the feedback loop is that you're rewarding the system, and then you're having it take actions that lead to the highest reward. And we'll get into some details of that. So again, if you just walk through here, there's some good explanations of each one of these things. And I think this is a good summary of the different components of deep learning. So I'll let you read that on your own. Now, the next thing that I'll mention is that this TensorFlow playground is a great way to get started with understanding some of the intuition behind a neural network. And in particular, one of the problems with neural networks is that they're very complex to understand, and it's hard to understand how to build something that's useful. And the reason why is that there's a lot of different things happening. And if you're writing software and you're trying to understand the intuition behind a neural network at the same time, you're solving a lot of things at the same time, which can really be confusing. And this particular TensorFlow playground is a great tool that allows you to get at the intuition of our neural network and to get into really write the details, essentially, versus focusing on code or building all kinds of different debugging techniques that have nothing to do with the neural network. So how do you use this tool? Well, you just click on this, play, and you can see what happens is that the test loss and the training loss are shown here. And so the training is the data that you're fitting the model on, and then the test loss would be after you fitted the model, how well does it perform? And so typically you would want these to be basically the same so that it's not overfitting. If you have a higher test loss than training loss, that means you have an overfitting problem. And the more the difference or the delta between those two things, the higher the overfitting. So you can see here, this is kind of stuck here, that it's pretty good, but look, now it's slightly overfitting here. And so this would be a good example where it took 796 epochs. So the neural network was trained 796 times over and over again. It learns something, it takes that information, goes back into the neural network, learns a little bit more, takes that new information that's combined from the last run, goes in, learns a little bit more, and it's learning through this. And a couple other things to point out is that what we're doing is the output here are the things that we're predicting, and then the input are the features. So this is what goes into it. So if you're trying to do a classification that's a binary classification, which is what this is, the input will be 2 and the output would be 2. And then the neurons in here, this is where the work is happening, where it's learning the information that it needs to solve the problem, to do the classification, and it's kind of going through over and over again and running through the problem. So how would we tweak this or change it a little bit? I mean, one improvement would be that we could try to reduce the computational requirements of this by maybe enhancing it a little bit. So it took 796 to get to 0. So could we speed that up? Well, one way you can speed it up potentially is you could tweak the learning rate. And what is the learning rate? So the learning rate is a way of telling the solver to grab more information so that it can, in theory, get to the optimal solution quicker. But the problem is if you set the learning rate too high, then you'll just oscillate back and forth, and you won't solve the problem. So let's set the learning rate really high here and see what happens, and see if the training loss or test loss if it oscillates. So we can see here, look, it does nothing, right? In fact, it makes it worse. It just sits there, and it's not able to identify the correct solution. It's just going to go back and forth because it's too large. It's learning too much stuff at the same time, and it's really bouncing back and forth and can't get to the bottom of the valley, essentially. So if we go back here, what if we make the learning rate? I think it was at 0.03. Or was it? What was the learning rate? Let me just refresh everything, and I'll start again just so I remember what the learning rate was. It was, let's go close this, and I'll open it again. And I think that, yeah, 0.03 was the default learning rate. So let's maybe make it, instead of extreme here, let's try a slightly higher, like 0.1. So if we run this, does that improve it? And that actually looks like it is pretty much, it's actually much faster to get to 0. There we go. So before there was 768 epochs, but because we tweaked a little bit this hyperparameter, we get to the solution much quicker. And so that's the art of deep learning. That's a little bit frustrating for people, is that a lot of times you're tweaking knobs and it's not exactly clear always if it'll work. And that also might be a good example of why AutoML could be a good solution for many neural networks that you're dealing with. Is it really worth your time to be tweaking this knob back and forth? Why don't you just try a tool that will automatically do this for you? And I think this is something that we're seeing more and more, is that a lot of these hyperparameter tuning techniques are less interesting to people, and they want to at first try out a solution by just running a script or running some kind of automation. So the other things that you could play with on your own if you want to get more up to speed is look at the activation function. So that's the actual code that's running each time the neural network is activated, and that's what you're actually solving. You're running this activation function, and then the other thing you can add is regularization. And what regularization does is it penalizes the solution so that it's less likely to overfit. And then you could also go and change as well your regularization rate. So those are things you can play with. You could also add other layers, right? So you could add another hidden layer. You could add additional neurons. So let's try that. Does that make it faster? For example, if I add another hidden layer, and we see that in fact that actually might make it even a little better, right? So we can see that by adding additional layers, we can get to the solution even faster. So these are all things that are somewhat non-intuitive, that unless you play around with it, it's going to be difficult to know. You also can toggle the different data types. So that was an easy one, but what if we pick something hard like this like pinwheel shape here? And if we train this thing, it's going to take a while to get to the optimal or to get to the lowest possible training loss. The other one is you can also do regression. So we were doing classification, but there's also some regression problems to solve as well. So I guess the main technique here is that I would recommend going through and playing around with this so that it gives you the intuition behind a neural network. Okay, another emerging topic here that we talked about generally using the last reference here is that this is a way of generating new data instances. And a good example of generative model is this GAN link here. Let's go to this link. And so this talks about what is a generative model, and it means generative adversarial network. And it informally, it means that you can generate new data instances, and a discriminative model can discriminate. And why does this come in to be useful? One, the generative is interesting because you can build things like music or new faces or maybe new movies, right? This might be a new technique that people are interested in doing. And the discriminative means that I'm able to show the difference between different types of data. And you can see this is really a probability definition, right? Is generative is the joint probability of something, and then a discriminative model is the conditional probability. And some of the other things that are interesting to think about here is that with discriminative and generative models, handwriting could be a good example of something you could play around with. So the overall structure of a GAN is that you have some generated data, and then you're able to actually use this discriminator to figure out which one's fake and which one's real. And as the training progresses, the generator gets closer to being able to produce output that can fool the predictor, right? So if you want to go more into these GANs and how they're useful for computer vision, these are some good links here. The next topic that I'll also cover is this music generation topic, which is a research topic from Google Research. And it's pretty interesting here. You can see there's another use case here where you have this timbre transfer. This enables new interactions with raw audio. So you can convert an input from your microphone into an instrument like a violin or a flute. You could do a music transformer, which generates new performances from scratch. GAN synthesizer generates high fidelity audio, all kinds of different music relationships here. So you can see how GANs this is an emerging topic, but you can build some really fascinating things with GANs, fake images, fake videos, or maybe some kind of synthetic form of entertainment as well. The other emerging topic in computer vision is this concept of using TF Hub, and let me talk about that real quick. And so what TF Hub is a way of grabbing things from that are already trained and then using them to generate new images. And what's neat about this is that this whole TF Hub system allows you to grab pre-trained models and use that information to generate new things here. And so this is a generating artificial faces with a progressive GAN model. So how do we use this thing? So first step is you go through and install the software. Then there's some basic imports here. We can see all the stuff here. And then I would load in from the TF Hub here. And let me just show you what that is real quick. So if I go to TensorFlow Hub, this is a progressive GAN trained on Celeb A for 128 by 128 images. So what's neat about this is that Google built this for you. And so this is an image generator trained already, and you, if you wanted to use this to make your own celebrity type morphs, all you need to do is use a few lines of code, right? This is just a couple lines of code here, and I can now use this to build something. And you could, what's neat about this, I mean, I guess if I could also open this in a separate notebook, is that I could kind of go through this hub where they have a whole list of repositories, and that's the same link that we're just on, and then build out different solutions. So I think this is one of the more interesting research topics, is to look at all these different models in here. And you can see there's TensorFlow JS models, which are JavaScript models, TF Lite, which would fit onto these edge devices, or Coral is right, which would be this. Like if I wanted to use the Coral image classification, and then also I could go by problem domain. So this is, I think, a very interesting new emerging topic, is this idea of I start my project with something that's almost like a sourdough starter kit, or like I'm building something that somebody else started for me. So that was just the overview of it. And then in general, what happens is that you would go through and use that to build out your own celebrity model, and then generate a transformation. So what does that look like? this would be, I think, the example is I could go through here and build this kind of face morph thing, and also what I could do is I could also use transfer learning as well. So these are the main technique here is that you're building from existing knowledge. So let me also show you how transfer learning could also be used. So we show GANs. You could use a pre-trained model with TensorFlow Hub, but another similar way to use information that somebody else has already trained on is transfer learning. So for image classification problems, in particular, maybe you don't have the time to build it, or it's too expensive, and so you can take a shortcut. And in this particular example, this is a fully trained convolutional neural network, and you can chop off the last layer here, the softmax classification head, and replace it with your own. And basically, you're using the work from an expert and just slightly tweaking it with just a little bit of code. So here we see transfer learning. You benefit from an advanced CNN, convolutional neural network, and the top researchers have built it on data sets that maybe you just couldn't afford to build. And in this case, you can see that this is somebody else's convolutional neural network. And then what you do is you just go like this, and you just chop off the last part of the neural network. And you're just treating it as a black box here. And then you're retraining the classification head only. And that's a transfer learning. So what does the code look like? In this particular example, you see that it's just a few lines of Keras. So I would make an import from Keras, and then I would put inside of here Keras sequential, and then swap out that particular layer. And just with that, I can get to 75% accuracy by using this solution. So there's a link to this notebook here that just shows just an overview of this. And here we go. There's some imports. There's my configuration. I grabbed that data from Google Cloud, and these are the different classes. I can read the labels and put them into a function, and then I see the pictures here, dandelion, daisy, all these. So then what I do is I build out a batch data set here, and then this is the part where you would go in and tweak and change that. So I would import this MobileNet model, and then I would build out my own customized version of it, because we can see I'm putting into this function the pre-trained model. And then you can see here that the training is pretty quick, right? Because it's mostly already been done, and you can see that I'm able to look at the model accuracy in a graph here, and then I'm able to do some predictions, and you can visually see the different predictions. So this is a pretty nice notebook that shows you how, with computer vision, you can use transfer learning to quickly get to a solution. So I guess that's the main takeaway so far. What we covered is that high level, their neural networks are the tool that really there's a lot of momentum around with computer vision, and in particular, it's complex to use neural networks, and a couple different solutions that can make things a little bit easier are, one is these GANs. You can use pre-trained models from TensorFlow Hub to make solutions with GANs. And that's one way to speed things up. The other thing is you can use transfer learning and slightly tweak it. And there's an example of this to use neural networks. So it seems like some of the direction that's headed with these emerging topics in computer vision is to do less work yourself and to leverage the power of these expert organizations. Like they could be Google, they could be a nonprofit, they could be, Amazon, but in general, doing less work to get better results is I think the trend right now with computer vision. So if you want to get more into that, you can go ahead and take a look at that. And I think that's just this section is just that notebook, I believe. So let's go to the next section here, which is Open Gym. So this is kind of an interesting and maybe experimental framework, which is this Open AI Gym here. And the way it works is that you have an agent. The agent will take an action in an environment, and then you will observe what it's doing, and then you will give it a reward. And the reward should incentivize the correct behavior. And if we look at Open AI Gym here, you can take a look at what this is. And this is a toolkit for developing and comparing reinforcement learning algorithms. And you can see how to install it. You need Python 3.5. You just say pip install gym. You can build it from source here. One of the environments that is kind of the bare bones basic one is this is the cartpool example. And it renders the environment at each step, and you should see a window pop up. And so here we go. If I click on this, there we go. We can see the cartpool. It's so we want to train this thing to be able to actually maybe stay in the center. And so how would we do this? This is the whole point of reinforcement learning, is that in order to make it better than random, you need to go and change these parameters. So the observation is an environment specific object. So it could be pixel data from a camera, joint angles, or a board state in a game like Pac-Man. The reward is a float. So this is the amount of reward received from the action that they took. And this scales different between environments, but the goal in training a model is to have the highest possible reward. And then in terms of done, this is whether it's time to reset the environment and train it again. For example, if you're in Pac-Man and you got eaten by the ghosts, then you're done. And then the dictionary here is diagnostic information useful for debugging, and the feedback loop here is agent, action, environment, observation, reward, and in general, it would look something like this. So the other example here, what I would do is I would put in this information, and then now if I run it, look, I can see that now it's standing up, right? So you can see I'm able to see it's been trained to perform better. And then these are just other examples of the different things that it can get into, and this shows the different environments. In particular, the one that I like is these Atari games. Could be kind of fun to play around with, and you can see these are old video games, and you can train them to beat the game by giving them different rewards. And so the one that I'll go through is this Pac-Man example here. So this is Open Gym demo. And if you wanted to go through and train your own Pac-Man model, some things to think about in terms of how to reward this would be, can you avoid ghosts? Do you want to eat the Energizer pellets? You want to go left? You want to go right? Do you want to randomly go some direction? What about regular pellets? Open spaces? And so there's some links here that can give you some ideas, but in general, this would be just some almost pseudocode that would give you some ideas. You could say from random, import choices, actions, eat pellets, make an actions list here, go through and build those out, and then maybe print out a series of steps that I'm going to go to. So If we want to run this inside of Colab, we can do that by doing these steps here. So pip install gem, go through and get this thing running, and then go to Pacman dependencies. So let's do that one next here. Here we go. And next we can go into helper functions. Let's go ahead and do that next. And these helper functions will just install boilerplate code like gem, TensorFlow, NumPy. So let's go ahead and do this. All right, and then I can create this virtual display here, and then this is a utility function that runs the MP4 file, and then we can do this. So here we go. Check out the action space and run it, and then this will run out the game. So if you were going to train this yourself, you know maybe first go through, watch it, see what it's doing. And again, that's an episode, right? When it goes through and it crashes. So if you want to build your own model that is better at this, what you would do is you would put in your custom code here, and then you would train it to have a reward. So, and then it gets into a strategy as well. So one of the issues with training something with reinforcement learning is that you want to optimize both the exploration and also the exploitation. And so the exploration is that first you need to know what's happening. Like you need to know what your environment is before you fully exploit. And so there's this combination of just randomly going places and figuring things out, which again can be very important, and then also going through and exploiting the solution that you've been able to pick up. So I think the best way to go to the next step in explaining this would be to cover AWS DeepRacer. So I'm going to go to AWS console here, and then we can get into a DeepRacer example. And I'm going to go to DeepRacer here. DeepRacer. And DeepRacer is pretty neat because it is actually a full simulation that also includes a physical component to it as well. And so you can learn the reinforcement learning, do all this stuff virtually, which has some value. I mean, the Pac-Man example I think is pretty neat, but it's even another story when you can actually apply it to a real world model. In this case, this would be a car, and you can also compete with other people in a virtual circuit. So the thing that I would do to start with is we'll click on this Get Started here, and then learn the basics of reinforcement learning here. So let's go ahead and take a look at this. And this is, I think, a very good example slide deck of what reinforcement learning is. So reinforcement is a type of machine learning where an agent explores an environment to perform actions, and those actions with good outcomes are the ones you want to reward, and you want to penalize or not reward the actions with bad outcomes. And reinforcement learning learns from experience over time and converges on the best solution. And this is different. And this is the other thing to point out, is that reinforcement learning is a different kind of machine learning. Most of the time, when people talk about machine learning, they're typically referring to supervised, which is I have historical data and I predict something from the historical data. Although unsupervised machine learning, still people, maybe the second most common, where you're looking at clusters that you're defining labels based on things you've trained. But reinforcement learning is a distinct fundamentally different than those two, like supervised and unsupervised. And it's different because of this. It's different because you have an agent. In this case, it would be the car, and the car does something. It takes some action, and then the action occurs in an environment. In this case, it would be the track, and then you look at what happened, and then you give it a reward based on what it did. So it's very similar to probably a pet, right? Where a pet, you would give it rewards based on it doing something good, and then you don't want to reward it if it does something bad. So if you tell your pet to come here, then you give it a treat. A very, very similar concept. Okay, so let's go to the next one here. How does AWS DeepRacer learn to drive by itself? So it's an agent that interacts with an environment with an objective to maximize its total reward. The agent takes an action based on the environment state, and the environment returns the reward in the next state. So how does this work? So the agent, in this case, simulates the DeepRacer vehicle in the simulation training. And then this embodies the neural network that controls the vehicle. So it takes inputs and deciding actions. So we had discussed this earlier, that if you want to get into the intuition of a neural network, one way to do it is to play around with that TensorFlow simulator. But in this case, we're actually training this agent using neural networks. And then the environment is a track that defines where the agent can go and what state it can be in. And this agent explores the environment to collect data to train the underlying neural network. So a state represents a snapshot of the environment the agent is in at that point in time. So for DeepRacer, a state is an image captured by the front-facing camera on the vehicle. So this camera is driving on the track, and then it can look into what's happening on the track, and then that's actually the state that it's in. And what are the actions that a car can take? It can take a lot of actions, but a couple of the main actions are steering and throttle. So if it goes left, that's one action. It goes right, that's another action. Throttle, how much gas do I give it? How much do I step back on it? And then a reward is the score given to the agent. So when it takes an action in a given state. And so in the DeepRacer model, the reward is returned by reward function. And you're going to decide how much based on the really what it did, right? If it does what you want to give it the highest reward. If it's almost like what you want, maybe you give it some reward, but not as high of a reward. And if it does something you don't want, don't give it any reward. So how would you do this? How to train a reinforcement learning model? So it's iterative. In this simulator, the agent explores the environment and builds up an experience. This experience collected are used to update the neural network periodically, and the updated models are used to create more experiences. So in this particular example with DeepRacer, we're going to train a vehicle to drive itself, and it can be tricky. So let's go ahead and say next here. And this is a really simple example of how to train this reinforcement learning model. So, I mean, ideally, you would just go straight, right? If it's right in the middle here, this would be the optimal outcome, right? Why would you want it to go over here? That's not the shortest path to the goal. The goal would be to go right in this pathway. And so how would that manifest itself in scores? So you can see that if you go right down the middle, you get a 2. So you get the highest reward that you can give. But if you start to veer off the track, the reward drops. And then if you go completely off of the track over here, then there would be no reward, right? So this is just an idea generally or conceptually of how you would think about which rewards to give the vehicle. And then in practice, one of the episodes is the first iteration. And so the vehicle starts to go, and then maybe it starts to veer off. And at first it gets a high reward, then it gets a lower reward, then it gets no reward. And then if you go off the track, that's it. The episode is over. And in this particular episode, you can see the total score is 2.2. and this, so we would want to train it again. We want to get more and more episodes, and incentivize it to get the highest possible reward. So here's a second iteration, right? And in this iteration, look, it learned, and so it goes a little bit better. So it goes, here we go. But now it veers off over here. So at least it got a little bit higher, right? So it's got a higher reward here. In this case, I think this would be, it would be 2 to 4, 4.4. All right, and so this is basically, the other thing that this points out is that iteration is how it learns. It can't just learn on one run or two runs. Is the accumulation of this that teaches it. And also, at first it needs to explore. So they also mention this up. Before you can fully exploit optimizing for the highest reward, you need to know what's happening, right? So that's why it's kind of going here and then it's going here, right? It needs to first know what the boundaries are, and then once it knows the boundaries of what's good and what's bad, then you can go through and train the reward. So what does this mean? It's exploration. So as the agent gains more and more experience, it stays on the central squares to get the highest reward. And so you can see that it says if we plot the total rewards from each episode, we can see how the model performs. So it should be the total reward or an episode should be going higher eventually. Like it's eventually going. There should be like a linear or super linear initial growth rate. Linear, super linear, exponential even, right? So this is slightly exponential for a second, and then eventually it'll peak out. Next up here, we have exploitation and convergence. So the more experience the agent gets, eventually they're able to reach the destination. And so this exploitation strategy, the vehicle will have a small probability of taking random actions to explore the environment. So here we go, there we go, there we go, right? And eventually the total reward, it would figure out that, okay, that's the best path to take, because I bounced around all over the place and I figured out all the edge cases. Okay, I don't want to go there. Finally, it figures out, okay, this is it. That's the best path for me to take. So this is a key component of training reinforcement learning, is that you can't just converge immediately. You have to first exploit the environment, and so you need to. You can't exploit it immediately. You have to explore the environment, and that's why, if you look at even things like a robotic vacuum cleaner, for example, that they will actually initially kind of explore the environment that they're in first, so that they understand what's happening before they try to get an optimal route. So this is a really part of an art as well as a science to train the reinforcement learning model. So what are the parameters of reward functions here? The reward functions include things like position on the track, the heading, the waypoints, the track width, the distance from the center line, whether the wheels are on the track, speed, steering angle, right? So you can see here that these are all different components of DeepRacer here. And these are things that if you're designing your own reward function, you can use one or more or all of these to define your reward function. And there isn't a perfect rule. It would just be up to you to decide how to reward it. So position on track here would be X, Y, right? So this shows you in terms of this left right coordinate here. That's one. The heading, like which direction are you actually headed in, and this shows you the angle. The waypoints, so this is where you're at. So each waypoint is really a step inside the route, almost like miles in a marathon. You're on mile what? the next section here is the reward function. So this is the track width parameter is the width of the track in meters, right? So we're going, and we can see how wide I am. And then the distance from the center line, there's either distance from the center or is left of center. And so you can use that to measure where you're at and do a reward. And then the other one too is, are all the wheels on the track, right? If you have one of the wheels off of the track, that might be a sign that you're not doing what you need to do, or maybe you do need to have a wheel off of the track because you want to have it be close to a curve or something like that. And then speed is another one, right? Is how fast is it going? Steering angle, like when you're turning the steering angle, how much are you turning? And so there's 13 parameters for this particular simulation. These are the different ones that you could use. And so in now that you know that, you could actually build out your own simulation. So that's why I think this particular framework is one of the more interesting ones, because you can write a Python function that's just a few lines of code here that lets you train your model. So here's an example. I would stay on the track, so give a high reward for when the car stays on the track here. And this example uses all wheels on track, distance from center, and track width. And so this function doesn't reward any specific behavior except for it just wants to keep the car on the track. So it's kind of a conservative model. So this might take a long time to converge because we're not letting it explore much. And if you look at it, you can see it in action here. You can see, and these make me a little bit motion sick when I look at these. Are like, ugh, because it's kind of going all over the place here, and it's learning how to explore, or how to converge. In fact, but it's doing very little exploration. But the function itself just looks like this, right? So it returns back the float value, and I just say if the wheels on the track and it's 0.5 times the track width minus the distance from the center, then what does that say? It says is greater than 0.05, then give a reward of 1. So give a high reward if no wheels go off the track, but by default give it a very low reward. So pretty simple algorithm, right, that you could build yourself. Next up, the reward function here, we follow the center line. So in this example, we measure how far away the car is from the center of the track and give a higher reward if the car is close to the center line. And so this one is a track width here. So here's an example. This is track width. And then this one is distance from the center here. And then we calculate 3 markers that are varying distance away from the center line. And then we give a higher reward if the car is closer and to the center line and vice versa. So here we go. If distance from the center is less than this marker, give a reward of 1. If the distance from center is less than marker 2, give a 0.5. And then I go through and I return back this float reward. So this one is more specific, and this one could learn the track pretty well, but it might be more poor at accelerating or braking for a corner. So it's basically designed to just kind of stay on this center line here and follow it, and that's the thing that we're rewarding. So again, tons of different strategies. There's not necessarily one perfect strategy for reinforcement learning. And then this is another one, which is no incentive. And why would you do this? Well, one, it's easy to program. You just return back 1. So that's kind of interesting. But what this would do is this would introduce a bunch of randomness to it. So the alternate strategy here is to feed it a bunch of random values, and these random values will allow you to basically be kind of erratic. And so this one is probably will make you the most motion sick, is just going all over the place here, because it has no rules. It's randomly giving you back a high reward. And so what this would do is potentially be able to learn more. You're optimizing towards exploring the track, but you're not necessarily. It could take a long time. It could take a long time to learn because you would have to explore everything about the track. But on the flip side, maybe you could learn something really good because of the randomness, and then you could use that technique. So now that's really the overview of this DeepRacer. And then if you want to build your model, let me show you a couple of steps here of how we would do that. So I'm going to log in real quick here, and okay. So here we go. All right, so in order to create a model, the first thing to do would be to learn from the environment. So in this case, a track, and this agent will take an action on its environment, and it will reward based on the state it's at. So how would we build one of these? We could just type in, new model. This is my model, like this. And then in terms of the environment simulation, I would pick which machine here that I would want to work with. So in this case, it would be a raceway track, or this kind of curvy track, and each one will give you different. You'll learn different things by training it on this track. If you train something like this, you might be training something that's really good at doing, going around turns. But if you trained it on this, you might get something that's really good at knowing how to go fast, right? And so this might be a really easy basic one to look at. Then we go through here, and then from here, when I'm creating the model, I have three different examples. I could do a time trial, I could do object avoidance, and I also could do head-to-head racing. And I think this is probably the easiest one to start with, is a time trial, where you're just going through the track here without having to do anything special. The object avoidance is an interesting concept, and what's interesting about this is that you have to take into account even more complexity, and what happens is that you're not only going to have to go through the track, but when you see an obstacle, you're going to have to detect that it's an obstacle and then go around it. And you have a couple different criteria here. So one is that you have a fixed location, and the other one is a random location. And then you also can go through and decide, how many objects you want on the track here. And then when you do go through and train it, for now there's only this one vehicle in the garage, this DeepRacer. But the third one that you could choose is this head-to-head racing. And then this is also kind of an interesting problem in that you can choose the number of vehicles that will that are on the track. And so you could say, 4 vehicles, and then you could choose a constant speed for the bots. You could make them go really fast or slower. You can enable lane changes. So you can basically add a lot of complexity inside of here. And again, you can pick which car you want. So these are all different kinds of things that you're training. And again, what's great about this is that once you train this, you also could apply it to your DeepRacer vehicle, your physical DeepRacer. So let's just pick time trial, keep it simple here, go to next. And then it's my turn now to build the reward function. So this is just kind of the default here to build. And you can actually build this directly into your code editor and actually play around with it here. And you can see it's pretty straightforward to try new ideas out. And you can also validate this, which is neat. Is like it could be easy to make a mistake, and I don't know, let's just put this in here. Let's make some bad code, and just do that. And if I validate it, in theory, that should not work, right? Too many values to unpack, right? So it showed me that I have some bad code. So that is actually pretty neat. There's also some reward function examples here. So you can see that it gives you time trial, fall to the center line, time trial, stay inside the two borders, time trial, prevent zigzag, right? So this one incentivizes the agent to follow the center line, but penalizes with lower reward if it steers too much. This will prevent it from going back and forth, right? Which we saw was kind of makes me sick a little bit when I look at this. And if I want to use this, I could just click this button and then start the thing I'm building into this. And you can see here that this might be a good starting point for me to tweak my model a little bit. And I think this is what's great about this particular simulation, is that it's a very straightforward Python function to tweak here. And this is the steering penalty threshold, right? So if the agent is steering too much, so in this case, if it's at this, then I can actually modify the reward. So once you do that, the other step you would do is go through and tweak the hyperparameters. And so this gets into some of those ideas that we talked about in the TensorFlow simulation, is that you can get into tweaking things like, okay, how many epochs do I want to run? What is the batch size of my gradient descent? Learning rate, so how much do I want to learn in each epoch? And then in terms of entropy, where do I start? Discount factor, loss type, these are all different knobs. They're like little knobs to turn to train my model. And then also how many numbers between each policy updating iteration, and then stop conditions, right? So set the stop conditions for your training job as well. So I won't do this because I've already created a model, but in general, if you use the free tier, you can see that you get some DeepRacer training time for free if you start off with an account. So you can see here, DeepRacer, you can create your own machine learning model, and you also can purchase this vehicle as well. And the free tier, I believe that you will receive 10 hours to train and evaluate models and 5 gigs of storage during your first month. This is enough to train a first-time model, evaluate it, tune it, and then enter it into the league. Right. So if you do enter the free tier, you can actually train a model completely by yourself and not have to pay for it. So that's something to consider. Now I have already done this, so I'm going to go back to my models and I'm going to look at one of these. Let's see here. Maybe this is one I did recently. New DeepRacer simulation. And what happens is once you've created the model, as it's simulating, it'll show you whether it's actually completed the lap, and also it will show you the simulation while it's actually occurring, and it's going through and showing you how it's navigated around the track and all those things. Now the RoboMaker logs themselves, you also can look inside of there and just double check that you actually have, you don't have any errors inside of your application. The other thing that's neat about the simulation as well is that it'll show you for each of the saved training runs, what were the hyperparameters, what does the reward function look like that you trained, and then also what's the action space. So where was it at in the track when you're training it, and then in terms of the let's see here, the actual finalized training, the other thing that it will show you is that it will give you back a reward graph that shows the number of iterations, and then also the best model that you've actually been able to get. So again, the goal is to optimize for the highest model here. And what it's doing is it's actually using the AWS SageMaker ecosystem to train the model, and then also using this thing called RoboMaker to simulate the agent's interaction with the environment. So this whole ecosystem is pretty powerful, and all integrated into this one platform. So I guess to maybe wrap this up, when you're done with this, what you would do is you could submit your model to this, to one of these virtual circuits, and you could say race again, for example, and submit your model here. And this would show, I could pick a model, I don't know, new DeepRacer model. I could submit my model here, and then what it will do is it'll show me how I performed against other people. And then I could decide, whether to train it again and try to beat the people that are in this particular race. So it's kind of an interesting concept, in that it's a full end-to-end solution that has a lot more depth to it potentially than just the OpenAI gym. And so if it is something you're interested in, you can do it completely for free by using the AWS free tier. So let's start to wrap up some of these topics here and cover the key highlights. So in a nutshell, what we covered today was these emerging topics. So let me put this here and make sure that I have the mouse on the screen. Okay. Just give me a second to connect this thing. Sometimes it takes a second to connect my mouse here. Let me double check. I think that's what the issue is. There we go. I think this will do it. Okay, so emerging topics. So the first in computer vision. So what are the emerging things that are happening that are fun? Is one is we know that deep learning is where a lot of the fun stuff is occurring. So deep learning is producing cool things, and one of the ways that you can get a better intuition for it is to use simulations. So we saw many simulations, and the simulations are great because they are low code or no code, low or no code, and I think this is very important to think about. Is are you really learning something if you're just stuck writing code all the time, where you can learn a lot more conceptually if you can focus on the actual problem? We also talked about the GANs, and so we know that GANs can do two things. One, they can predict fake data, and that's one thing they can do. And they also can create fake data, right? So what's useful about a GAN is the real world use cases could be new forms of film, right? So we know that that the film industry might use these things to create new forms of film or entertainment. We also know that they could be used to make more training data. So let's say that you're training something and you're getting stuck with, you don't have enough raw data to train a model. You could create fake data and train your model against the fake data. And we also use it in music, right? That's another example where people are using it. And we also talked about this TF Hub, which is an interesting emerging topic, which is that you're able to leverage models that are pre-trained. So these are pre-trained. We also can integrate into Keras. That's another neat thing about TF Hub. We also know that it's a good starting point for even GANs, right? You can build a GAN from TF Hub. So what's the summary here is that you can leverage expert knowledge. Expert knowledge. That's the key takeaway. The other topic that we got into was transfer learning. So transfer learning is interesting because with transfer learning, just like we were talking about with TF Hub, is you can actually take something that's really complex that someone built that probably is maybe not reproducible by the layperson. It's too complex for many reasons, either the technical complexity or the computational complexity for the data or power that you have. And then with transfer learning, you could actually modify, let's say 1% of the model, and then tune based on that. So 1% tweak to tune the model, right? So the other thing that we got into as well was reinforcement learning, or RL, right? And so with reinforcement learning, what you're doing is it's a lot like a pet or a child. And what you're doing is you have a feedback loop, and the feedback loop is that you are giving somebody a reward based on some action that they took, and then you're also measuring the state that they're in, right? So in the case of the car, right, we have the car track here that you want them to stay on the track here, and you're giving them different rewards. This is 2, this is 0.2, this is 1, based on where, how well they performed according to your reward function. So what's neat about all this is that some of these things can be applied to real world problems, and I guess in general, that's maybe the next thing that I'll just discuss very quickly is what is actually doable right now, and where's a good place to spend your time. So maybe this is we'll call this low-hanging fruit. Low-hanging fruit for CV, for computer vision. So what is the low-hanging fruit? If you want to solve a problem and help your community, for example. So first of all, what are the use cases that that you can use computer vision for. One is your community, right? This is, I think, something that I see emerging is maybe you're helping people with sorting trash, right? That could be a really helpful tool. Either you help people in your community, maybe with the pandemic, you help people. Maybe you're building, security systems. There's I think a lot of the use cases for computer vision are around a community and being helpful, right? So how do you help people by using technology? And then also another use case as well would be around non-network prediction. So what I mean by that is that you have something that's offline. That's another interesting use case for an edge-based computer vision device, is that maybe you're building something that doesn't require an internet connection because the model has been already deployed onto the device. So then how do I implement some of these things? I think the takeaway here is that if you're building something for these use cases, the tools that you can dig into can include looking at pre-trained models. I think this is one of the ones that is not utilized as much as it should be. But why would you build something poorly where someone already built it better than you did, and it's free, right? So I think this is something to think about in terms of the tools is, are you using pre-trained models? Another one is, are you using high-level tools, right? So are you using the best tools that you can? And so this I guess is a subcategory, and I'll just say B1 would be AutoML. I think is a good example of this. Is that in many cases, like Google AutoML, Baidu has AutoML, Azure has AutoML. A lot of these, Ludwig is another one. We'll get into this. Is that maybe initially is better to use something that just does a proof of concept and builds it out first. Another high-level tool is a cloud environment. The cloud can be a great way to build things with computer vision. And then another one as well is these hubs, like the model hubs, like TensorFlow Hub, like TF Hub, is why not leverage these automatically? Additionally, another tool that's available for computer vision as well is the framework. So in the system. So are you using something that has a framework integration to a cloud platform? A good example would be SageMaker. Almost everything in AWS platform now uses AWS SageMaker. Likewise, if you go to Google, almost everything they have is using TensorFlow. So you'll see that there's a tight feedback loop. And I think a lot of times it's easy to get stuck. Where I see people being stuck with computer vision is that they're not looking at these use cases. And there's other use cases too. And or they're not using these techniques, these tools. And in particular, the more, and we'll get into this later, one of the more interesting topics is this is AutoML, and the ways that we'll get into this. We'll cover Ludwig, which is a great way to do computer vision with almost no code. Also, the Apple environment has something called CreateML, and so you can build and train a model very quickly with CreateML. And then another is Google AutoML as well. Google AutoML. all of these are high level tools that at least should be considered when you're building something out initially to speed it up, to speed the feedback loop. And I'll wrap up with kind of tying all this together. And what I would recommend is to think about the concept of DevOps plus computer vision. And so what does that mean? So DevOps plus computer vision means that you're embracing this concept of continuous improvement, speed, culture, and it's all going together. You're building this model. So you've got automation here. You've got speed. You've got continuous improvements. And then you also have a culture, and the culture is making sure that you're getting things done properly, that you have good teamwork, those kinds of things. And how does this fit into computer vision is that if you think about this, if the core concept here is that, these are questions to ask when you're building a model, either for this class or for a company, is what am I doing? What am I building? And then the other question is, does anyone care? And then another question is, does it work? And I think for computer vision, this is a good feedback loop. Is okay. What am I building? And then does anyone care about what I'm building? And then does it work? And a lot of times I don't see this when I see somebody building something. This is the wrong. So this is the correct questions. But what I see a lot of people do is this would be incorrect questions. Would be, how complex is it, right? Incorrect questions is like complexity. It doesn't matter, right? How complex something is. Who cares how complex it is? First, what are you building? Does anyone care, and does it even work? Another one is what framework? Who cares? Who cares what framework? That's a wrong question. Or another one is how do I tweak the neural network layers, or like get into some a technical detail like a neural network complexity. All of these are not the point of building a solution. What you want to do when you're building a product is build something that is going to help community, solves a problem, and works, and is quick. And this is where the DevOps lifecycle comes in, is how quickly can I build something, iterate on it. Each week I should be making progress on it. But an easy way to not make progress is to focus on how complex you can make it, which framework you're using, get really deep into the weeds. These are, at some point they come up, but they're supporting to the core issue. If you focus on the supporting issues versus the core issue, then you're going to have problems. But if you focus on the speed and the problem, then probably what will happen is you'll use higher level tools at the beginning, then later you can decide whether you want to get into these complexity issues or get more into neural networks or what framework you use. But focusing on the problem, I think, is one of the other areas that I think is showing up in terms of edge-based machine learning. Okay, so that's probably a good spot to stop for questions. So maybe I'll stop sharing here and see if anybody